This time we are to find the foot of the perpendicular given the equation of a line expressed as L is equal to P plus your vector V, and you have here your x at 2 and negative 3. So the first step that I would like to consider here is I would like to show you the graph of this. Probably it's not necessarily a part of this step, but before we can solve the foot of the perpendicular, so that we would know the or probably some come up with some predictions on what would be its location. Let's try to plot that in the Cartesian plane. Our x, assuming that our grids are 1, so we have here 1, 2, and 1, 2, 3. This is where our x is. It's actually 2 and negative 3. Our point P is at negative 2 and 1. So it's actually your point P is here. Sorry, that's your point P. Negative 2 and 1. But of course, we don't have the line yet. The line could of course always do it like that or go it like this here. So we don't know that. But we do have a direction vector of actually 5 and 2. So for that, let's try to connect all of these concepts. This our vector V. Okay, we'll be also using this item later on is actually 5 and 2, right? So that would mean this is our V sub 1 and this is our V sub 2. If we're going to transform it to a normal vector, why do we need to do that? Because in a normal vector, it's actually identified as A and B respectively. So our normal vector is actually negative of V sub 2 and V sub 1, which will give us a result of a negative of 2, and then you have your 5. We're doing this because this is actually our A, this is our B. For our line, expresses ax plus by plus c is equal to 0. And we'll be able to add additional point or probably another intercept here in order for us to really graph this on our Cartesian plane. Again, it's not necessarily the part of this video, but I'm doing this for us to really connect all the lessons that we have. So if we have here ax plus by plus c is equal to 0, our a is negative 2, and let's use the point P here as our x is negative 2 plus b is 5 times 1 plus c is equal to 0. That's actually positive 4 plus 5 plus c is equal to 0. So 9 plus c is equal to 0. Our c to complete the equation is negative 9. Hence, our equation is actually can be expressed as negative 2x in general form plus 5y minus 9 equal to 0, or if you don't like a negative leading exponent multiplying all terms by negative 1, you will have here 2x minus 5y minus 9 equal to 0. Again, we're doing this because I would like to find out the x-intercept for me to really illustrate that on our Cartesian plane. So let y is equal to 0, so you have 2x minus 5 times 0 minus 9 equal to 0. 2x minus 9 is equal to 0. Sorry, this should be plus 9, right? As we multiply all terms by negative 1. So you have 2x is negative 9. X is actually negative 9 halves. So our x-intercept is at negative 9 halves and 0. So that point is actually somewhere here. Negative 9 halves is negative 4.5. So we have 3, 4, 5 somewhere here. This would be our x-intercept. This is actually negative 9 halves and 0. So I did that because I would like to really provide us with the picture of how would be our foot would look like, or where can we locate our foot. So connecting these 2 points, this is now our line. This is our line represented by the equation L is equal to negative 2 and 1 plus your direction vector of 5 and 2. So if this is our x, and x is when connected to the foot will come up with a perpendicular line. So probably if I'm going to assume our foot is somewhere on the first quadrant, assuming that my line here is straight, assuming it's in the first quadrant. So we'll be expecting our foot is here. That's our f. That's what we are going to solve here. So hopefully all of these are clear. And by the way, don't worry, some of this will be used later on as we move into the formula, because the formula for our foot is actually x, the given x, minus x, sorry, this is actually expressed in this manner, the inner product of x minus p, and p can be the point P itself or even the x-intercept, and then the normal vector, a unit vector, times your unit normal vector. And this is actually already integrated in identifying the normal vector here. Okay, so let's start with the unit normal vector because that's the only item that is not there. So it's actually the ratio of your normal vector and its length. Okay, please review the video discussing this because it's already there as well. So the length of our n is actually the square root of the square of the first components and the plus the square root of the square of the second component. Our first component a here is -2 squared. The reason for that, okay, it's here. Okay. Then plus 5 squared. So you will have the result here. That's actually 4 plus 25. So square root of 29. That's our length. So for the unit normal vector, you will have your normal vector, which is this one, but we will be using the parentheses. Okay, so again, reintroducing that. Usually we express it this manner, but since we are talking about the foot now, let's use this parentheses, but they mean vector as well. It's not a point. So we have here -2 5 over square root of 29, or other references will have -2 over square root of 29 5 over square root of 29. This is the unit normal vector to be implemented here. I hope that I have much space. If I don't have much space, I will be actually using another page for this. So we now have our unit normal vector. Our P is already given earlier as this one here, and our X is this. So we can now determine our foot of the perpendicularity or the intersection of the line L and its normal line, which would pass through X. Okay, so let's do it like this. Hopefully you're still following. So our X is at, what was our X? 2 and -3. 2 and -3. By the way, we are expecting somewhere in the first quadrant, so that's your guide. We have our guide for that. So you have minus, you have here, so let me write it at the bottom because this might be very long. Minus, your X is 2 and -3, minus your P. Your P is at -2 and 1. So you have -2, sorry, it's a point, right? 1. Your unit normal vector, sorry, my space is really not enough, so let me bring it down for a better discussion. So you have X is 2, by the way, let's do it again, -3 minus 2, -3 minus your P, which is again -2 and 1. -2, 1. And then your unit normal vector, -2 over square root of 29, 5 over square root of 29. We're getting the inner product of that. Then multiply again. Take note of this. Multiply again with unit normal vector, -2 over square root of 29, 5 over square root of 29. Don't worry about the square roots. You don't need to rationalize that. Later on, you would see a magic of that being removed. So you'll have here 2, -3, minus. So you will have here the result with 2 minus -2 is 4. That's 4, right? And then you will have here 3 minus -1 is -4. Then your unit normal vector 2 over square root of 29, 5 over square root of 29. Again, -2 over square root of 29. This is outside. 5 over square root of 29. Okay. Still 2 and -3 here. Okay. That's 2 and -3. This time, inner product. So you're just going to multiply the first components and add with the product of the second components. So if I'm correct, that's 4 times -2. Whether this is minus. Okay. 4 times -2 is -8 over square root of 29 plus -4 times 5 is -20 over square root of 29. The result is a scalar times your unit normal vector. You have here this. So let's add first 2, -3 minus, you will have here -28 over square root of 29 times your unit normal vector. And this time, I would assume that it's clear that the square roots will be removed, because as you multiply that here and here as scalar, you'll be removing the square. That's why there's no need for us to really simplify or rationalize the denominator at that point. So you have here minus negative 28 times this is positive 56 over 29 now. Square root times square root is already removed. And then negative 28 times 5 is minus 140 over 29 still. Now this time we have 2 points. Simply combine them. So you will have to write 2 minus 56 over 29. And then you have here negative 3 minus negative 140 over 29. And let's see if this would really be at the first quadrant. You may use your calculators there. Okay, so I have here 2 minus, you will have 56 divided by 29. So I have in rational expression, or I mean in fraction form, 2 over 29. And the other one is negative 3 minus negative 140 divided by 29. That's very large, so we're expecting for it to be positive. So you will have here 53 over 29. Both positive, so probably our assumption earlier based on our representation is correct. That's our foot, and it's there on the first quadrant. To be more specific, if you would like to use decimal notation, so you will have the first result, 2 divided by 29, approximately, again, we're just using approximation, 0.07, rounding it off into 2 decimal places. This is not exact, just an approximation. 53 divided by 29 is actually 1.83, still approximation. We're doing this because you would like to really see the possibility of our assumed foot earlier in our graph to be near exact. So 0.7, take note it's here, so it's not yet 1, so, and it's even really closer to our y-axis, so it's closer to 0, that's correct. And 1.83, so probably the only problem with my graph is it looks like it reaches 2, but it's somewhere here, okay, so it doesn't reach 2, so 1.83 is close to that. Now, this is now the foot of the perpendicular. Take note, we just introduced these steps here just to make the discussion clearer and to illustrate that in the figure. Okay, so the foot is actually starting here, but it uses the normal vector which is already introduced here earlier. The normal vector can be solved using the direction vector, the vector or direction vector of the line where our P is included, and the foot of the perpendicular is also included. Thank you very much for watching.